Hello, I am Jim Potvin, and in this short video, I'd like to introduce you to our Works Ergo software package. I want to talk a bit about the philosophy behind it, the approach that we take, some of the innovations, and the science behind it. So when we look at physical ergonomics assessments, there's typically a number of inputs that are required. First are we designing for males or females, body mass stature, so anthropometry. We normally set the percent capable. Most Ergo software packages don't have age. We want to include that in Works in the future. But you also need to know things like, is it a static task, a lift, a push, a pull? Are people seated? The frequency and effort duration, so you can calculate the duty cycle. And then we have some of the geometry here. So where are the hands? What's the orientation of the hands? What kind of grip is being used? And typically we look at the location of the hands relative to the midpoint of the ankles on the ground. So here we would say, how far forward the right hand is, or how far forward the left hand is, or the height of either, and how lateral or medial they would be. And then for things like lift and lower, we also might need to know the distances that the load is being carried, whether there's any twisting or coupling. So most Ergo tools will include some combination of these. And these diagrams and throughout Works, you'll see that the right is indicated in orange and the left is indicated in blue. Here we can see in the yellow arrows the orientation sort of the knuckle direction. So either going to the person's left or upwards. And then these pink arrows show the direction of the palm. So these are some of the things that you'd need to know. Is somebody drilling? Are they grabbing a handle? And where would those hands be in space? And then usually an Ergo tool, you'd then have to posture the person relative to this. So the ergonomist would have to guess what posture the person will be in, or maybe you have a photo of how someone did that one particular time that you observe them for one particular individual. So with those inputs, we can look at some of the assessments that currently get done. So I'm going to just do a sample analysis here of a very simple task. This is someone lifting a box with these dimensions. They're reaching at about 35 centimeters, so 0.35 meters. The hands start at about 10 centimeters up, 0.1, and go up to a height of 0.85 meters as they put it on a table. This might be done once every 2 minutes, so about 210 times per day. I typically think of a work day as being 7 hours of work, and then 2 15-minute breaks and a 30-minute lunch in an 8-hour workday. So 420 minutes, so about 210 of these per day. Let's say it takes 1 second, just to simplify, to do this lift. The load is 55 newtons in each hand. And let's just say that there's not enough of a space to do a full power grip. So they maybe have to wrap 3 fingers inside a slot in this box. So a very simple task, a lift from floor to table, or what we think of as a floor to knuckle lift. Now in ergonomics, I typically think of risk as being the balance between the demand on a system and the capacity to meet that demand. And I talk about this more in the DCR video that's available to you, the demand capacity ratio. But here, if the demand, for example, the compression demand on the spine, or the cardiorespiratory demand, or the torque on the shoulder is greater than the capacity for the population that we're designing for, which is usually 75% of females, then you might say that the risk is unacceptable. So when we do a complete ergo assessment, so here we have our lifter, here we have our demand capacity balance scale. Now, when I would do an analysis, I may use something like 3D SSPP or some digital human model to calculate compression, so around 3,000 newtons here. I could also do a neck analysis. Not many people do a neck analysis, but we have that in the Works software. And when we see things in this sort of fuchsia color, we would say that that's the demand that's being output. So here's the demand, and then we could compare that to some capacity. Some might use the 3,400 newtons from NIOSH. Here in the 3D SSPP, they would show you in a table the moment demand. They'd show you the capacity of an average person, and then using the standard deviation, you could then maybe calculate either the capacity of a 25th percentile female, so that 75% would be capable, or what this software does is tell you the percent of people that would be capable of 8.6 Newton meters if the the average strength was 32.1 plus or minus 7.3. You could also use my handpack software to input the demands on the fingers and also the type of interface, the frequency, the duration, and it would tell you that the capacity to meet that demand for the specific population would be 132 newtons. You could also use my arm force field method. This is a spreadsheet that I make available to anyone who's interested. And this uses the hand location relative to the shoulder and the force direction and the force magnitudes and frequencies, and calculates manual arm strength, so the maximum strength, and then corrects that for my MA equation. And you can also see that it corrects for subacromial impingement that might occur based on a relatively recent paper I published with David Rempel. You could use the Liberty Mutual manual materials handling equations, which I developed with Ciriello, Snook, Maynard, and Brogamus in 2021. And these are now sort of digital versions of the tables, and also include a lot more research than was originally available in 1991 when that method came out. And they use things like reach and vertical height and frequency and the displacement. You could use the Liberty Mutual Dempsey metabolic equations to look at the metabolic demand here, and then you could compare that to some capacity that you've evaluated. And many people still use things like Rula to evaluate this posture. I don't ever recommend using Rula to make a decision on a task, but it could be used to quickly triage where your issues might be and where you'd want to spend all the time it would take to do this type of analysis. So once you do all of these analyses for this simple lift, you would then maybe have a compression in newtons and a moment for the neck in Newton meters, and strength demands and capacities for the hand, metabolic cost in kilocalories a minute. You could use our RCRA method to determine the cumulative demands in terms of the number of seconds of recovery you need. And so here I'm showing anything highlighted is what's output from these different methods. And then sometimes you would have to go get your own capacity. So we would use 3260 for a 45-year-old female based on Yager's data. And then you'd have to kind of go through and say, okay, is the demand under the capacity? Yes, so we're going to call that acceptable. This demand is under the capacity, and so on and so forth. You could go through and compare each of the demands to the capacity. And in each of these cases, other than the Rula, which tends to be quite conservative, you would see that the task would be considered acceptable. So a lot of work and effort to go in for a simple lift, to do a detailed analysis of all the body regions to make sure that this task is acceptable. And that takes a lot of time, and people can have different opinions about what posture the person's in, so they may get different compressions and arm demands for the exact same task. So when we look at the current state of ergo analyses, we'll see that some of the methods will use very old tools. And so some of the very prominent methods that you may use will use things like the Romert equation from 72, the Garg metabolic equations from 78. Still a lot of them uses Stobie strength data from 82. It's a very good database, but there's been a lot of strength data collected since then. Many still use the Snook and Ciriello tables from 91. Many people use the revised Naish lifting equation from 93, and I've published a paper to explain why you probably shouldn't do that. Things like Rula and the strain index. So that's one of the problems with many of the tools, is the data is quite outdated. It's not even from the 21st century, which we're 23, 24 years into now. They typically don't have a hand. They graphically have a hand, but they don't have any hand capabilities. They may have some wrist strengths, but no hand capabilities, and all tasks are done typically with an interface with the hand. They don't have very good estimates of manual arm strength. I published a paper with Hall et al. In 2021, and I won't get into the details here, but basically these are strengths that we measured, and then these are the strengths that were predicted by the 3DSSPP software, and that's the same algorithms that get used in Siemens Jack and Process Simulate software. And there's almost no relationship between the measured strength and the that estimated. And these the software was tailored to the individual's strength to try to give it the best chance to predict strength as possible. So there needs to be other methods that get used. And finally, they do all kinds of analyses, but they don't integrate those for the user. So you need to, almost like I showed here, you need to go and do each of these assessments yourself, and then ultimately come back and make a decision, sort of taking all this data yourself and figuring out what to do with it. Another problem, and a big one, that people don't think about is usually only one posture is assessed. You may look at a couple anthropometries, but you would then assume some postures. So some ergonomists would say, I think somebody's going to do it this way, or they have a photo that someone happened to do it that way one time. And that's not necessarily how people work. People do things in different ways. And so in Works, for this same task, we would look at a whole cluster, maybe 12,000 different feasible postures that don't violate certain rules, like the center of pressure isn't outside the base of support, you don't go through any physical barriers, and none of the joints exceed any of their ranges of motion. So what's the benefits of movement variability, and why might people do things in different ways, both within themselves and also between themselves? So task performance variability is inevitable, even when individuals try to minimize it. So there's been studies in the lab and even in the field where they've asked people to do things the same way and they can't. But task variability can utilize different degrees of freedom, different muscles, different joints, put loads on different parts of tissues. So that's an advantage. And putting loads on different muscles or switching between muscles can delay muscle fatigue development, and that will reduce the risk of work-related musculoskeletal disorders and serve to perform performance. So quality is maintained as well when people aren't fatigued. So posture variability happens, one, because we can't help it even if we wanted to, and two, it's good for us. And so people will naturally do things in different ways. So the question is, why do we ignore posture variability in ergonomic assessments? And the simple answer is, it's a lot easier than analyzing 12,000 different postures. But maybe not quite as reliable, because different people, we've studied this, the same ergonomist given the same task once a month for 3 or 4 months will pick very different postures and swear that's exactly how someone's going to do it, even though it's not the same as what they guessed a month before. But picking one posture from many feasible postures increases the probability that different practitioners will, one, assume different postures, as I just mentioned, and by virtue of that, get different answers, and by virtue of that, make different decisions. And 1 month, you might say the task was acceptable, but because you picked another posture the next day or the next month, you might say it's unacceptable. So, and this even happens, like I said, within practitioners. So this is where our Works software comes in, and I want to just go through some of the innovations that are associated with it. One is that we try to use only fairly easy to measure variables that most ergonomists have learned. Things like reach and height, things like hand orientation are fairly easy to observe and need to be input. There's no posturing of a mannequin, and so you are essentially allowing the software to pick all the feasible postures, and then we've come up with ways to deal with that variability. And so we are hoping that it's not just going to be accessible to ergonomists, but also engineers and worker representatives will be able to use the software. And the outputs are unique in that they evaluate every feasible posture. No software except for maybe my backpack software, which I started selling back in the mid-90s, which was looking at just sagittal plane lifting, have done that, I believe. It embraces the variability in task performance and the associated variability in injury risk, because it performs all feasible analyses on all feasible postures. It fully integrates the results from the best current tools, and some are very up to date. And we calculate these demand capacity ratios, which I'll explain, and have a separate video that goes into detail about that. And it can be utilized to analyze a full job with multiple tasks, and I'll talk a bit about that later. So when we look at the different inputs that might typically get used, I've sort of described all of these already. The only difference with Works is that there is no posture that needs to be, and that's the thing that takes people the longest and is probably the least reliable. We do need to know where the hands are in space. We need to know what kind of grip they have and what the orientation of those hands would be and where the contact point is. So all of these measures are what people typically learn to do in ergonomics, but you don't have to guess at a posture. So this is when there are no barriers. And so when there are no barriers in the way, we will assume that you're going to indicate where the hands are relative to the midpoint of the ankles. But if there's a barrier like a table or a box, like I showed previously, all the measurements are the same except for the anterior measurement is taken with respect to the barrier, so the front edge of the barrier, because we're going to assume someone's going to get as close as they can until their toes get close to it, or their knees, or their hips, or whatever it happens to be for that particular posture. We have standard digital human model with multiple segments. We'd make some assumptions based on the literature as to where the centers of gravity are, what percentage of the total body weight is attributed to each of the centers of, or each of the segments. And we use the very recent NHANES database to estimate body mass and stature for 5th, 50th, and 95th females and males. And this just shows you some of the power of works. So here would be our lifting task from the side and from behind and from above. And you see the variability, especially in the elbow and shoulder postures, as well as the trunk postures. Here, there would be less options for variability for a task where the hands would be like this with a tabletop as a barrier seated. Here would be just a generic static task where somebody is pushing up with the right hand. And here would be a pushing or pulling or carrying task. And so all of these can be assessed. And one of the main things is, we think that ergonomists have done a good job at looking at the variability in sizes of people, maybe the variability in capacities of individuals. And so, the Snook and Ciriello data shows what the full variability, that table I showed you from 3D SSPP has sort of means and standard deviations. So for different body parts, we could look at the full range and then sort of set our cutoff at the 25th percentile. But what we don't do a good job at all is looking at the variability in the demand on individuals. And I think that that's something that really needs to be considered. So we clearly do that by looking at the multiple postures that are feasible with works. The other side of it is the output. So what are the ergo assessment tools? First thing is we've fully integrated the linear force modules of the Handpack software. And so that's now fully integrated from my company, Potvin Biomechanics. We calculate lumbar compression and shear forces in a fairly traditional way. We have a neck analysis. We're sort of developing a neck pack to go with Handpack, but we also currently have some strength data in there based on posture. We use the arm force field for manual arm strength that I developed with Nick Ladelfa at Ontario Tech University. And this is a much more accurate way to predict arm strength than the methods used in software like 3D SSPP and Process Simulate. I recently developed an above shoulder tool with David Rempel in 2022, and this accounts for work done overhead and the impingements that might occur in the shoulder and corrects the strength, acceptable strength values for that. And we also use the Liberty Mutual manual materials handling equations, which I had the pleasure to be involved with developing. We'll be integrating the metabolic equations of Dempsey. We use the MAE equation to correct strength for the duty cycle and account for fatigue, and the recommended cumulative recovery analysis that I developed with Murray Gibson at Auburn to combine the requirements for recovery for multiple tasks. So if we look at demand and capacity here, we can see this is just a generic table. Let's say this is a different example than the one I showed you already. And so basically what we do is we divide the demand by the capacity. And if the value is over 1, it means the demand is greater than the capacity for the population that you're designing for. You would have a DCR, demand capacity ratio, over 1, that's shown in red. And then I could do the same for each of these. So 10 divided by 22 is 0.45. That would be acceptable. 75 is less than 90, so it's about 83%. But these are higher. So anything in red here would be considered to be unacceptable. As well, we look at the feasible postures. So here, for this particular task, there will be over 12,000 feasible postures. And so for each posture, we would have a separate shoulder demand and a separate compression and a separate neck demand. So I just want to quickly show you how that would look and how the demand capacity ratios would be handled. I do a separate video on DCR ratios that you can look at in more detail, but I'll just go through this quickly here. So for example, with all these different postures, we're only showing 11 of the 12,000. There would be a posture that had the lowest compression of about 2573 newtons, and one that had the highest compression of 4908. Now, a lot of times ergonomists will try to find the perfect posture to prove that the job can be done safely, but that doesn't mean that people can possibly replicate the same thing every time. But we also know that workers probably won't use the worst possible task if they have experience, or worst possible posture. And so what we do is we calculate the full range of compressions. Here would be the limit I would set for a 45-year-old female. And so we see a certain percentage of these, about 40% are under that limit, and about 60% are over. So the question is this task acceptable or not? What we recommend currently, and we're working with some partners to create some validity for this, is that we would use the 25th percentile risk. So people can't do it in the best possible way, but they're probably surfing somewhere down in the optimal range. And of course, what might be optimal for compression may not be optimal for the shoulder. They may be at counterpoints to each other. But in this particular case, the 25th percentile compression of 3,000 is under the limit, would have a risk score of 0.92. And so we would consider that this task would be acceptable because there would be at least 25% of the feasible postures that could be done in an acceptable way. The 50th percentile, I think, is probably a little bit too conservative because, probably skilled workers aren't going to be surfing around here, but that would be considered unacceptable. And so right now we're recommending this 25th percentile be used. And so what we do is we find a representative posture close to the 10th, the 5th, the 15th, the 25th, all the way up. So there are 11 of those. Any postures that are considered to be under this line are shown in green, and these postures up here, the representative postures, are shown in red. And the one with the thick mannequin is the one at the 25th percentile. So this is just showing there might be other postures close to this, but a representative posture. So if we use the work software and we come back here and we take these inputs, if you remember, we had a lot of work that we needed to do to calculate all the demands and capacities so that we could make a decision about this task. In the work software, I do a whole video on this interface, so I won't spend a ton of time on it, but you'd pick your anthropometry, so 50th percentile female. This is lifting a load 210 times a day. We would define this barrier here. I've just shown a blown up version, so we'd have to define this box. And you can see here that the load, you can see that the reach is 15 centimeters forward of the box, and it starts off at a height of 10 centimeters from the ground. So at the bottom of the lift, it's 10 centimeters for both hands. And at the top of the lift, it's 85 centimeters or 0.85 meters. And from above, you can see that the left hand is about 18 centimeters left, and the right hand is about 18 centimeters right, so at shoulder width. The forces are 55 newtons. We've got the 3-finger pull. We can imagine that the knuckles would be facing forward if seen from above or from the side, and that the left palm would be facing to the right, and the right palm would be facing to the left. And so you can define that here. No gloves would be used. And no other things like bracing or limiting the trunk, which again, I go into more detail in the other video. So I click on the calculate button. I get these outputs, which you've already seen this figure here. You also would get a body map showing you the representative demand capacity ratio for the right and left hand, the right and left arm, compression, the neck, and Liberty Mutual where applicable. And then there's an overall score. So if this overall score is less than 1, it means that each of the body parts had at least 25% of the postures that would be acceptable. And these are also just ranked in order so you can quickly see the limiting factor here. And we also output an Excel spreadsheet. I do a whole separate video on the Excel reports that have all the same information that you input and all of the output data, as well as some more granularity in terms of how these DCR scores, like that graph I showed you earlier, how they change. So this black line would be for compression. So most of them are underneath the limit for compression. And finally, another advantage of the software is that you could look quickly at the risks for a 5th female, a 50th female, and a 95th female, or also do all of the males and see for this particular task, the limiting factor would be the 95th male. These have all been assumed to have the same mass, so it's not because this one's heavier. It's just because some of the postures they need to get into because they're longer levers put them at a higher risk. And so just to kind of show you the benefits of work quickly, first thing it does is predicts all feasible postures. So it's got a higher reliability between users. And then it fully integrates the ergonomic assessment methods. So it only uses the most current valid tools. And it has a much more accurate arm strength estimates using the arm force field. It includes the hand and fully integrates the hand pack linear force aspects, which most tools don't have. It accounts for muscle fatigue using the MAE equation, and also can be used to combine tasks, like if you're lifting from multiple levels using the RCRA method. And it's the only tool that it can incorporate, if you choose to, the above shoulder corrections to account for impingement. So this has just been a quick video to introduce you. I do other videos on the overall interface, both for the inputs and the outputs, the Excel reports and what you can get from that, as well as just this concept of the demand capacity ratio, which is be new to people, especially when considering, up to 12,000, 20,000 different demand capacity ratios for multiple body parts. So I thank you for your attention and hope you'll consider taking a look at the work software in a little bit more detail.